Okay, so here's some notes about transformation. Okay, in geometry, a transformation comes in 4 different types. We have 3 of them on here to begin with. They are, of course, translations, which we're going to talk about today. Rotations, which we're going to talk about tomorrow. Reflections, which we're talking about today. And then one more called a dilation, which we're not going to talk about until tomorrow because dilation doesn't go with one of these 3, right? These 3 are special types of transformations called isometric. Isometric. Okay, these are isometric transformations, or sometimes just called isometries. Okay, this is a vocabulary word that you should learn about. Isometric transformations or isometries. Okay, they are called isometric transformations because the objects remain congruent. Okay, nothing changes about their shape, nothing changes about their size. Okay, the image is congruent to the pre-image. Okay, so those are some things that we need to talk about also, those 2 vocabulary words, which are image and pre-image. Okay, pre-image and image. Okay, so the pre-image is like a landscape, something naturally that happens in the world, right? And you see it and you say, oh, that's beautiful, let me take a picture. Okay, the picture is the image. Okay, so the pre-image is what happens first. You have some picture somewhere, you have a landscape, you have in geometry a triangle or a quadrilateral on a grid. Okay, that is your pre-image. And then you do some type of a transformation to it. And the resulting thing is called the image. Okay, just like the picture on your phone is an image of what you have in real life, this thing that comes after transformation is the image of whatever the original shape was. Okay, so a pre-image is what happens first. You perform a transformation, and the result is the image. Okay, and oftentimes the image is shaded. Okay, we're going to color in the image the end product of what happens after a transformation. Okay, so let's come back here and talk about this. Translations are an isometry, of course, isometry, because it preserves size and shape. Okay, in fact, this also preserves orientation. Okay, preserves orientation. So if we have a triangle that's vertex up, the vertex will always be up under a transformation or a translation. Okay, translation moves all of the points of a figure, so every single one is affected by this. The same distance in the same direction. So all the points go to the right, all the points go up, all the points go down, all the points go left. We are applying this translation to all of them. And orientation is preserved, which means the orientation doesn't change. Okay, and we're going to see what that is like here in a second. Okay, so we do all times a translation under some type of a rule or notation. Okay, it's telling you how far you are translating each point in what direction. So we're going to have a rule for the x direction. Plus goes right, minus goes left. And we're going to have a separate rule for the y direction. Plus goes up, minus goes down. So let's look at example 1. Here we have ABCD, right? This is a triangle clearly put on a grid. And we're going to translation 3 units down and left 5 units. So let's start at point A. And we count, because it's on a grid, we count 1, 2, 3 units down and 1, 2, 3, 4, 5 units left. So let's talk about how we write this, because this is our original point A. Okay, so that's A. And what we do here is we write it as A prime. Okay, A prime. We put a little tick mark up above the letter A, because now it's a new point. So A prime is the translation of point A. Okay, and then B prime down 3 and left 5. We have B prime, so you put a little tick mark there. And then C is also goes down 3 and left 5. C prime. Okay, so all of your new points after a translation or after a transformation have a new notation. It has a little prime deal on it. So then you connect your dots. Bless you. Connect your dots, right, to make your figure again. And then we are going to shade in this image. So we can decide which one was the pre-image because it is not shaded, and which one is the image because it is shaded. Okay, so now let's write down the notation. Okay, and this is usually how you're going to see the problem presented. Is we have moved in the x direction 5 units left, so that's x minus 5, comma. And we've gone down 3 units in the y, so that's y minus 3. Okay, so we subtract 5 from every x coordinate, and we subtract 3 from every y coordinate of your original 3 points in order to get your 3 translated points. Okay, sometimes this is called a glide translation because all of these points are kind of gliding from here to here. And if you connect them, of course, you can kind of make a 3-dimensional figure or whatnot right there. Okay, kind of fun to do if you're into that kind of stuff. Okay, here's our second example, translating up 5 units, or up 4, and then right 5. So once again, we're going to count from each point. We're going to go up 4 units and then right 5 units and plot our new points and shade that image. So there is your image, right, like that. Okay, so now let's look at the notation. Right, we do the x part first. So the x said we go right 5. So that's x plus 5 as your x notation, and the y is up 4, so y plus 4. Okay, so usually we're going to start off with this as your rule, and then you will have to translate your image from your rule or from the notation. Okay, so one last example about A prime. What is the translation shown here? So let's look at point A. We're going to count how far to the right or left it has gone, or let's see, maybe point C. Let's do point C. Point C has gone 1, 2, 3, 4, 5, 6, 7, 8 units to the left. And let's see, so it's gone 1, 2, 3, 4 units up.
So x minus 8, y plus 4.
So the notation would be x minus 8. You subtract 8 from every x term, and you add 4 to every y term. Okay, so our translation is given to you by a rule that tell you how far to go left or right and how far to go up or down. So now we have a little bit of algebra, right? There's no graphing here, so let's do some algebra. Our rule says we're going to add 12 to every x term, and we're going to subtract 5 from every y term. So let's do that math in our head. So -1 plus 12 is 11, and 8 minus 5 is 3. Okay, and we're going to do that to each one of these 4 points. So we're able to write the coordinates if you know the rule and you're beginning with coordinates. Okay, so that's really all there is about translations. So now let's jump over and look at some reflections. Reflections are in isometry. A reflection creates a mirror image. Okay, if you're looking in the mirror, right, your right ear is on the, well, I guess the left side of your face if you're looking from the other direction. Right, your things are switched. What was on the right is on the left of your image, and so on and so forth. So the image of a figure across a line or an axis of reflection.
What is that? Mirror?
Mirror. It's a mirror image of a figure across a line of reflection. Okay, so a line of reflection. We have to have a point that we're going to reflect it across. Right? We have to have a middle to do it. Orientation is once again preserved. No, orientation is reversed. Okay, and it depends on the type of reflection about the type of reversal. So let's see what happens. We're going to reflect this across the x-axis. So our x-axis is the horizontal axis, I hope you know. Right, this is the x-axis right here. So this is a top to bottom reflection. Okay, so everything on top of the x-axis is going to be reflected to the bottom below the x-axis. And everything below the x-axis gets reflected to the top. Okay, so it's changing from top to bottom. So let's see what we can do. Basically what we're doing is we are counting how far away are each of our points directly from that line of reflection. So let's start with A, and we're going to count directly to the x-axis. That would be 1, 2, 3, 4, 5, 6, 7. A is 7 units above the x-axis. So our reflection is going to become 3, 4, 5, 6, 7 units below the x-axis. So here's A prime down here. So our coordinate was 3, 7 for A, and then A prime became 3, negative 7. So this is A, and that's A prime. Okay, B was at 2, 3. So B is 3 units above the x-axis, so its reflection becomes 3 units below the x-axis, which is at, let's see, 2, negative 3. And then C is, of course, 7, 1, so C prime is at 7, negative 1. We are counting directly towards our axis of symmetry, or our line of symmetry. So here we have to shade our image, right, so that we know which one came first and which one got, in this case, reflected. Okay, so A prime was on top, so now A prime is on the bottom, right? So it's a top to bottom reflection. Orientation has been reversed. What was on top is now on bottom. So let's look at what the rule can be. Okay, what happens to the x-coordinate from A to A prime? It stays the same. So in our notation, across the x-axis, the x value stays the same. But what happens to the y value as we do an x-axis? It turns to a negative. So we're going to change the y value to a negative. So every point across an x-axis keeps the x value the same, but the sign of the y value changes to a negative of whatever it was to begin with. All right. Now let's look at the y-axis. So here's the y-axis reflection. Here is your y-axis. Now we're going from right to left or from left to right, depending on where we start. So once again, we're going to count how far have we gone, how far are we away from the line of symmetry. So A is 1, 2, 3, 4 units away, so A prime is 1, 2, 3, 4 units away on the left side. And we do a similar thing with B. B was 3 units to the right, so now it's 3 units to the left. And C was 8 units to the right, so now C is 8 units to the left. Okay, so when we're doing a y-axis reflection, which coordinate does not change? The y-coordinate does not change in a y-axis reflection. But what happens to the x-coordinate? It becomes negative. It changes sign. So in a y-axis reflection, the y value is preserved, and the x-axis becomes its opposite. So if it's positive, it becomes a negative, and if it were negative, it would become a positive. Okay, so now let's get to the tricky ones. The line y equals x. Okay, so from your Algebra 1 class, the line y equals x is the 45-degree line that goes through your origin that has a positive 1 slope. So here is the line y equals x. It has a positive 1 slope, and it goes through the origin. Okay, so you still are counting how far away are we from those points. Okay, and we're going to count diagonally. Since this is a diagonal line, we're going to count the diagonals. So let's look at B. Let's start at B. It's closest. How many diagonals away is B from the line y equals x? 1 diagonal and 1/2. This is 1.5 diagonals away. So we are not counting vertically or horizontally. We are counting diagonally. Or if you're a Harry Potter fan, Diagon Alley. So we're going to be 1.5 units away from the axis of symmetry on the opposite side. They're at B prime. So we're counting diagonally. How many diagonals do you count to get from point C to the y equals x line? So here's 1 diagonal, 2 diagonals. So this point C prime is going to be 2 diagonals away on the opposite side of your line of symmetry. Okay, we have a diagonal line of symmetry, so we are counting diagonally. So A is 1, 2, 3, 4.5 diagonals away. So it's going to end up 1/2, 1, 2, 3, 4 diagonals away from your line of symmetry. So now let's draw our figure here again. Okay, do it as good as you can and then shade it. So let's see if we can figure out what this rule is for our y equals x translation. Okay, so let's write down the coordinates. A was at the point 0, 9. Where did A prime end up? At 9, 0. Interesting. B, point B started out at 4, 1. Right, 4, 1, 4 in the x and 1 in the y. And where did B prime end up? At 1, 4. Maybe I'm seeing a pattern here. C was at the point 8, 4, and C prime ended up at 4, 8. So what would our rule be for a y equals x line of symmetry? Right? They're going to switch. The y becomes the x becomes the y. Okay, your coordinates switch positions. The y becomes the x becomes the y. Okay, in algebra, we call this an inverse, right? Your x's and your y points switch. When you're doing an inverse or an inverse function, your x's and your y switch. So a reflection across the line y equals x is an inverse reflection. You switch your x and your y coordinates. Whatever they started with, they're going to switch to become the image. So the last one, we have the line y equals negative x. Okay, so that's the negative 45-degree line that goes through negative 1, 1, negative 2, 2, negative 3, 3. Right? All of your points that are on a negative 1 slope through your origin. So that's the line y equals negative x. It has a negative 1 slope from your origin, so left 1, up 1, left 1, up 1. And then also down 1, right 1, down 1, right 1. That's a negative 1 slope. So we are still counting diagonally. So how many diagonals is point A away from your axis of symmetry? And that would be 4.5 again. 1, 2, 3, 4.5. So we're going to end up at 4.5 over here. Here is A prime. Okay, we'll do a similar thing for B. B is 2.5 diagonals away. So it's going to end up at 2.5 diagonals here. And let's see, C prime is 1, 2, 3, 4, 5, 6 diagonals. So 1, 2, 3, 4, 5, 6 diagonals to get to C prime. Okay, so do your best to connect your dots. Maybe you want to have a ruler or use the edge of your phone and shade. So once again, let's see if we can come up with a rule for your points. So A was at the point 0, 9. A prime ended up at negative 9, 0. Okay, B started out at 4, 1. B prime ended up at -1, -4. Okay, point C started out at 8, 4. C prime ended up at
It's turning the
-4, -8. So not only do the x's and y's change position, but they both become
negative.
the opposite sign. So positives would become negatives, negatives would become positives, and of course zeros would stay zeros. Okay? So we are counting how far away is each of our points from your line of symmetry, right, perpendicularly. So if it's an x-axis, you count vertically. If it's a y-axis, you count horizontally. And if it's a diagonal axis, you count diagonally to do your rotate or your reflections. Okay, so remember, these are both called isometries because the image is congruent to the pre-image. That is all. Thank you very much.